Hi guys, and welcome to this video. Within this video, we're gonna see the basic definition of an interrupt, as well as the different steps supported by the Cortex-M microprocessor to switch from the main program and start executing the first instruction of our interrupt handler. An interrupt on its basic definition is just a signal received by the processor, and based on its priority, the processor may decide or not to interrupt the main program. If the CPU decided to interrupt the main program, then it will switch from the execution of this main program to executing the secondary program part of this interrupt service routine. Once the processor finalizes the execution of this interrupt service routine, it will jump back from the interrupt handler to the main program flow. The same definition and concept is applicable as well for the case of Cortex-M interrupts. Now, in terms of execution flow within the Cortex-M microprocessor, we need to execute a couple of stages to properly switch from our main program to the interrupt service routine. First of all, the CPU needs to do some partial saving of the processor context within the current active stack. Partial saving means we are saving the scratch registers like R0, R1, R2, R3, R12 register, link register, program counter, and XPSR register within the current active stack. Once done, the CPU will set the link register with this magic value xreturn. This xreturn will be needed later on to properly jump from the interrupt service routine back to our main program. The third stage consists of two sub-stages. First of all, the CPU may decide or not to switch the current execution mode. The Cortex-M does support two execution modes, handler mode and thread mode. Your main program may execute in handler or thread mode. However, the interrupt service routine will execute always in handler mode. Hence, if your main program was executed in handler mode, then there is no need actually to switch the modes. However, if your main program and typically actually executed in thread mode, then the CPU will need to switch the mode from thread mode to handler mode. Now, the third sub-stage consists of switching or not the stack pointer. In Cortex-M, there are two stack pointers, process stack pointers and main stack pointer. The interrupt service routine on handler mode will use always the main stack pointer. However, your main program may use the main stack pointer or the process stack pointer. If your main program was using the main stack pointer, then there is no need actually to execute this stage. However, if your main program was using the process stack pointer, then the CPU, of course, will need to switch the stack to the main stack pointer before jumping to the interrupt service routine. Finally, the CPU will need to retrieve basically the interrupt service routine handler address to be able to jump to it. This interrupt service routine handler or function, it is part of this vector table. The vector table is kind of lookup table, and each entry of this vector table will correspond to a pointer or address that is pointing to the corresponding interrupt service routine function. Hence, based on the interrupt number, the CPU will be able to index properly the corresponding entry within this vector table, and then retrieve the address of our handler and then jump to it. So guys, this is our Keil-Mdk project. It is C-based one and has been compiled for an ARM Cortex-M based platform. The hardware that we are using is an STM32 microcontroller. Right now we have already compiled the project and loaded the binary into the STM microcontroller flash memory. We started already Keil-Mdk debug session. Now the program consists of updating the Systick timer registers to be able to trigger a Systick timer interrupt. We'll try here to analyze the different steps that have the processor taken to be able to switch properly from the main program to our Systick timer handler. And we'll try to match what we will see here to what we have learned within the slides. Now, we'll try to analyze first of all the current state of our main program. Now, our main program is executing in thread privilege and using the main stack pointer. This is the first thing. Second thing, this is the value of our link register. This one, once we jump basically to the interrupt service routine, will be updated with this magic value xreturn. Also, those registers will be saved into the current active stack area, And to be more precise, we'll have a partial saving of those registers like scratch register, R12, link register, program counter, and XPSR register. Now let's try to jump to our interrupt service routine. Now we are within our Systick handler. First of all, we need to analyze our stack area. So we copy this here. This is what's already available there. Now as you can see, this is matching R0, this is matching R1, this is matching R2, and this is matching R3. So far so good. This is matching actually R12. Then we have the link register. If you remember, the link register that we have written down before we jump to this handler was 0x08, 0000, then 1C7. So this is already matching. Then we'll have the program counter that will hold the address at the moment that the CPU decided to switch from our main program to the interrupt service routine. And finally, we'll have the XPSR. So far so good. This partial saving has been done properly. Then we will see that the link register has been updated with this magic value xreturn. This xreturn magic value will be needed later on to jump to properly jump back from our interrupt service routine to the main program. Now in terms of modes, our main program was running on thread mode. On interrupt service routine, the CPU will switch to handler mode. So this is done. However, our main program was using as well the main stack pointer. Hence, there was no need actually to switch or to use a different stack pointer. So the same stack pointer has been kept. Finally, and this we don't see of course, the CPU will read out the vector table and fetch basically the address of our Systick timer handler out of this vector table. Which entry to use from this vector table is based actually of the number of our Systick timer. This we'll see in further videos, but our Systick timer has number 15. Hence the CPU will look into the entry number 15 within this vector table, and then we'll be able to read the base address of our Systick handler. Then we'll know which location it must jump to. And this of course is matching what we have seen already within our slides. Thank you.